Okay, we're given a problem about the region bounded by r equals sine theta, where theta goes from 0 to pi. And we want to find the area of the region. First thing we want to do is we want to sketch the region. Now this should be a very straightforward exercise, having done the previously chapters on polar coordinates, which should have been done in previous courses, but we chose to go ahead and do some review on that. Okay, we do this region, and the idea is very simple. We let theta go from 0 to pi, and we find points whose coordinates are r theta for every angle theta. So we draw a series of lines representing different values of theta, and we know that sine theta, as theta goes from 0 to pi over 2, which would correspond to going from the theta equals 0 position to the theta equals pi over 2 position, the values of sine increase. So as we go from one angle to a greater angle to a greater angle up to pi over 2, the distance from the axis, the r coordinate, is going to increase. Now we also know a little bit more about how the distance increases, and we can use well-chosen angles like 30 degrees, 45 degrees, 60 degrees, or the pi over 6, pi over 4, pi over 3 angles, and get the coordinates of some of these points. For example, we would have square root of 2 over 2 pi over 4, because when theta is pi over 4, sine theta is square root of 2 over 2. That might be one of the points on the graph. Maybe not one of the ones I've indicated, but be fairly close to this one. Okay, well, we use those techniques, and I'm not going to go over those techniques. We've been over them already, and it's, again, something that should have been done in high school courses and repeated in college level pre-calculus, but unfortunately sometimes gets left off. Okay, well, you have to know this. You have to understand polar coordinates. I made the point in class. You're not going to understand what happens in spherical coordinates if you don't understand polar coordinates. You're not going to understand cylindrical coordinates either, but that's actually fairly easy once you understand polar coordinates. You have to understand the principle of this thing in order to understand spherical coordinates at all. Okay, well, we want to get the area of this region. So how do we get the area of the region? We take our typical delta r by delta theta increment, which looks like this: delta r this way and r star delta theta this way, where r star theta star is any old point in this region, assuming we have a small region. And as we've seen before, the dimensions of this region will be delta r by r star delta theta. It corresponds to an angular increment delta theta and an r increment, and we've pictured that previously, so I'm not going to talk a whole lot about that. So the area we know to be r star delta r delta theta. Now we know that for the region that we're talking about, theta is going to go from 0 to pi. I told you that. And r within this region starts at 0 and ends at sine theta. So r goes from 0 to sine theta. The total area then is going to be the sum over all these regions. Now we're going to have theta increments running from I equals 1 to n. We just we partition the interval from 0 to theta into n sub intervals, and we get a bunch of these. Okay, so for example, the way I've drawn these, if we use these as our partition, we have 1, 2, 3, 4, 5, 6, 7, 8 intervals of theta. So I would go from 1 to 8. And within each of these, we would partition our r variable. Okay, so for this region, for example, we would have a sequence of r intervals going from here out to here, and the typical interval would correspond to this. Okay, so if this is our typical interval out here, it's a little wide, but if this is our typical interval, it's got area. What? Take delta theta and multiply that by r star, where r star is an r value within this region, times our delta r, which is this. That's going to give us our area for the reasons that we've already discussed. So for every one of these theta intervals, we're going to partition r, and they're going to be, well, we're going to have m sub I intervals, and it's m sub I because we're going to partition r for every theta interval. So, you know, theta intervals go from 1 to n, so your typical r interval will go from j equals 1 to m sub I. In this case, we got 1, 2, 3, 4, 5, 6, 7, maybe 8, 9 r intervals. It's a little ambiguous the way I drew these. So for this particular theta, this would be theta, let's see, 1, 2, 3, 4, 5, 6. This is our sixth theta interval. So this would correspond to I equals 6. And we would have 9 r intervals within that sixth theta interval. So we would go from j equals 1 to 9 for this particular, for I equals 6. Okay, I equals 6, it's our sixth theta interval. And then for that sixth theta interval, j would go from 1 to 9, so m sub 6 would be the number of j intervals you have in the sixth, the number of r intervals you have in the sixth theta interval. Okay, well, that's the meaning of this thing, and you should know that. You know, you've done this in first year calculus. That sum is going to represent our area. And that sum, if we take limits as our delta thetas and delta r's go to 0, leads us to the, well, okay. Let's just take the limit as our delta r's go to 0. Then each one of these will become an integral of r with respect to r. R sub I, delta r sub I becomes r dr in a process that you should understand. And r goes from 0 to the sine of theta sub I. Okay, so that this sum becomes this integral. Then we take the sum, we take the limit as our delta thetas go to 0, and now our integral goes from 0 to pi with respect to theta of the integral within here. Now, I haven't given you a full explanation of that. Don't want to do that right now. If we really need that, I can detail that. But we did detail that kind of reasoning in rectangular coordinates, so hopefully you can understand that reasoning as it applies in polar coordinates. I could draw a three-dimensional diagram and everything, but you've already seen that, so I'm choosing not to do that at this point. In any case, starting from our typical delta r by delta theta interval, we get an expression for the area, and then we sum that over theta intervals, and for each theta interval over the corresponding r intervals. And we approach a limit, which is this integral. And the integral is going to give us the area of this circle. And this actually does end up being a circle. It's got a radius of 1/2, a diameter of 1, because clearly from 0 to 1 is a diameter. So its area, and if you actually do the integration, you get pi r squared, which is pi, I wrote down 1/4 because I was squaring it already, pi times 1/2 squared, which is pi over 4. Okay, that's kind of blurred out there. That's a 1/2 though. Okay, well, in the next video, we're going to look at what happens if you've got a z function. The z function is going to be 1 minus r squared, and we're going to try to find the volume of the, well, the volume between the xy plane and the graph of z equals 1 minus r squared. And we're going to build that up by starting to look at typical delta r by delta theta interval with a sample point and so forth.